Hello, Mr. Baina here, and welcome to the second law of thermodynamics. The first law of thermodynamics describes work. Work is completely converted into heat, or heat is completely converted into work. Now look at this system. This is a piston. This is a gas. When heat is applied, the gas expands, but this weight represents the work. When weight are now placed into the piston, it pushes the piston down. Therefore, the internal energy is given by the final internal energy minus the initial internal energy, or E. And that is equal to the heat that is added into the system minus the work. So this is the first law of thermodynamics. Now in this case, work is actually positive when it is done by the system, but work is negative when it is done into the system, such as weight. The weight is now acted into the system, therefore work is applied into the system, whereas heat, when it is added into the system, it generates work. So that is how work is now being applied by the system to produce work outside. But in the contrary, the reverse one is that work is being added into the system, thus making a compression into the piston. So however, that is the first law of thermodynamics. But this is not always true, because according to the second law of thermodynamics, that is actually formulated by Rudolf Julius Emanuel Clausius. According to Rudolf Clausius, the energy of the universe is constant, and so the entropy also of the universe tends to be at a maximum. And so what is entropy? This second law of thermodynamics that was postulated by Rudolf Julius Emanuel Clausius is actually based on this postulate of Sadi Carnot. Who is Sadi Carnot? Sadi Carnot is a French engineer. He is the founder of science of thermodynamics. So basically, Sadi Carnot is the father of thermodynamics. He's the first to recognize the relationship between work and heat. So again, Sadi Carnot is described as the father of thermodynamics. Sadi Carnot actually postulated his first law of thermodynamics by the use of the analogy of a steam engine. The steam engine works by transferring heat from a warm reservoir to a cold one. This is a Carnot cycle, the Carnot cycle that was postulated for the first law of thermodynamics according to Sadi Carnot. And in here we have the pressure and the volume diagram. And this is a piston. This is a gas chamber inside a piston. And so in the first process, step 1 is an isothermal process at the highest temperature. So T at H. So in other words, if it is an isothermal process, there is no increase or decrease in temperature. However, the pressure is now dropping, while at the same time the volume is increasing. So in this way, heat is being added. The heat is coming from the source or the reservoir. And then for step 2 is that there is a tremendous pressure drop, but it is an adiabatic process wherein it does not dissipate heat into the environment. It also do not absorb heat into the environment. So basically, on the third step is the releasing of this heat from that piston into a reservoir, such as the environment. And so now the last step is an adiabatic process again, wherein the pressure is again increased at a significant amount, but there is no heat exchange into the environment because it is an adiabatic process. So this is how simple it is, how work and how heat is being added into the system and basically produces the work. This is the first law of thermodynamics that is proposed by the father of thermodynamics, which is Sadi Carnot. While it's true that there is the first law of thermodynamics, but according to Rodolphe Jolyus, Emmanuel Clausius, that the second law of thermodynamics states that heat cannot always flow itself because it requires that heat will be flowing from a colder body to a hotter body. And so the second law of thermodynamics is actually entropy. So what really is entropy? So the second law of thermodynamics can be stated in three equivalent ways. Number one, heat flows spontaneously from a hotter to a colder object, but not vice versa. In other words, colder object cannot release heat going to a hotter body. So this is the first principle of the entropy or the second law of thermodynamics. So look at the illustration here. So the first principle of the second law of thermodynamics is actually a hotter body will release heat going to the cold body with a distance L and a cross-section area of A. So this is how the principle of heat transfer works. And the second statement to the second law of thermodynamics is that there is no heat engine that cycles continuously and can change all of its heat into useful work, because remember that according to the first statement that heat always flow from a hotter body to a colder body. In other words, that engine will always produce heat, and heat of that engine cannot be useful to doing all of the work, but rather the rest will be dissipated into the environment because heat again travels from hotter object to a colder object. So the first principle of thermodynamics, or the first law of thermodynamics, is that heat or energy can be converted into another form of energy in such a way that heat can be used to produce work. But this is not always the case, because the second law of thermodynamics states that yes, it's true that it can be converted into a useful work, but the rest of that heat can be dissipated into the environment, or maybe it can be absorbed by a colder body instead of producing everything of this quantity into work. Therefore, the work done now is that heat from a higher higher temperature minus heat that is dissipated into the colder temperature or colder reservoir. And finally, the third statement for the second law of thermodynamics, also known as entropy, is that if a system undergoes a spontaneous change, for example, from ice converted into liquid, it will change in such a way that its entropy will increase, or at the best remains constant. But in other words, this only points out that there is always an increase in entropy, meaning the second law tells us that the manner in which a spontaneous change will occur, spontaneity, in other words, like ice now converted into liquid, while the first law tells us whether or not the change is possible, the first law deals with the conservation of energy. But this is not the case in the second law, because the second law deals with the dispersal of this energy. That is why ice becomes water, and the randomness of the spontaneity will always occur, and that is entropy, meaning the loss of energy, and also known as the disorder. So again, what is entropy? Entropy is actually the measurement of the degree of randomness of energy in a system. In this case, the lower the entropy, the more order it is. For example, this has a very low energy, and then the randomness and the arrangement of the atom or molecule is much stable and order. But as the increasing number of energy that is uh, produced within the system, such as this one, the more it is random and the more entropy or the more degree of randomness is being released into the system, or that is associated within the system. So the lower the energy, the lower the disorderness of the or the randomness, and then the higher the energy, the higher the entropy is, and then the higher association of the degree of randomness that is occurring within the system. And so here's another meaning for entropy. Entropy is given by the symbol S. It is a state variable for a system in equilibrium. By this, it is meant that S is always the same for the system when it is in a given equilibrium state, like equilibrium in pressure, equilibrium in volume, and internal energy, or U. The entropy is a characteristic of the system at an equilibrium. So when the change of heat enters a system, an absolute temperature T, which is in Kelvin, the resulting change of our entropy is given by the formula. The change of entropy is always associated to the change of heat over the absolute temperature. Provided the system change is a reversible way, for example, the process is reversible from water going back to ice, or from ice going to melt into water. The SI unit for entropy is given by Joule per unit Kelvin. A reversible change, this is a process, is one in which the values of pressure, volume, temperature, which is absolute temperature, and internal energy are well defined during the change. If the process is reversed, then the pressure, volume, the absolute temperature, and internal energy will take on their original values when the system is returned to where it started. So in other words, entropy can be both reversible and irreversible. To be reversible, a process must usually be slow, and the system must be close to equilibrium during the entire change. Another fully equivalent definition of entropy can be given from a detailed molecular analysis of the system. If a system can achieve a particular state, what particular state is it? Example, the state of pressure, volume, absolute temperature, and internal energy, in which omega, the different ways, meaning the different arrangement of the molecules, because this is actually the entropy now, the randomness. For example, then the entropy of the system or state is given by another formula. S is equal to K subscript B, the logarithm of our omega. Where ln is the logarithm to the base e, and our K subscript B is the Boltzmann constant, which is 1.38 times 10 to the minus 23 joules per Kelvin. Entropy is a measure of disorder. It is a state that can occur in only one way, meaning one arrangement of its molecules. For example, it is a state of high order, but a state that can occur in many ways is a more disordered state. So, for example, our ice that becomes water, the molecules will become disordered. One way to associate a number with disorder is to take the disorder of a state as being proportional to our omega. And remember that we have a formula for this now. The number of ways the state can occur because our entropy now is given by K subscript B logarithm to our omega. And entropy is a measure of, again, disorder. So when you speak of spontaneous process, such as ice is now melted into water, that's a spontaneous process in a system that contain many molecules, always occur in a direction from this one, a state that can exist in only a few ways, to a state that can exist in many ways. Because we do not really cannot see how molecules exist in a different random or the randomness as it occurs. Hence, when left to themselves, the system retain their original state of order, or else it increases their disorder, in other words, increasing entropy. So I keep on utilizing the problem about ice, and this ice becomes water, and it will produce the randomness of the molecular structure from ice to water, because that is the principle of entropy. And so here we have a 20 gram of ice is precisely at 0 degrees centigrade, because remember that water becomes ice at 0 degrees centigrade, and at the same time ice starts to melt at 0 degrees centigrade. And that ice melts to water with no change in temperature, meaning to say it is a latent heat of fusion. There is no increase in temperature. So it is a latent heat. By how much does the entropy of this 20 gram mass will change in the process? Now, by slowly adding heat to the ice, we can melt it in a reversible way. The heat needed is delta Q, or the change in heat. And remember that the change in heat for latent heat of fusion is the mass of our ice multiplied by the value of the latent heat of fusion, which is mass is 20 grams, and the latent heat of fusion for ice is already given, a standard one, which is 80 calories per gram. And so we can cancel out the grams, and we will get the value of 1600 calories. And so we will bring this value to the formula for our entropy, and the formula for our entropy is delta S, and delta S here is now equal to the change of our heat over the absolute temperature. And so the change of our heat is already given, 1600 calories divided by the absolute temperature, which is 273 Kelvin. And the value becomes 5.86 calories per Kelvin. And that will be all equal to, if we convert this into joules, it becomes 25 joules per Kelvin. So this is now the amount of entropy of the 20 gram mass of ice that is now processed at its randomness because of the melting of the ice. So this is actually the entropy, the energy that is lost in the conversion of ice to water. So notice that the melting increases also the entropy, and at the same time the disorder. So how much is the disorder being computed? It is 25 joules per Kelvin. Now here is another problem. Here we have a piston and we have a gas, and the piston is now being pushed so that it will compress the gas, and we have the force that is applied in here. This is our figure 21.1, and I want you also to focus on figure 21.2. This is a two system that has a hotter object and a cooler object, and definitely a hotter object will travel heat transfer from hotter object to a colder object. But we will see that one later on as we apply this problem into a statement in the next slide. So as shown in figure 21-1, that is the one with a piston, an ideal gas is confined to a cylinder by a piston. Okay, you remember that one? And that piston is now being pushed down slowly so that the gas temperature remains at 20 degrees centigrade. So it is an isothermal process wherein the temperature is maintained. But during the compression, 730 joules of work is already done onto the gas. So the question is, what will be the entropy change of the gas? The first law tells us that the change of our heat is equal to the change of our internal energy plus the change of our work. Now, this is the first law of thermodynamics formula. But because the process was isothermal, meaning to say there is no increase of temperature, this is also no decrease of temperature, the internal energy of the ideal gas do not change. Therefore, our delta U here will now become 0 so that we can convert all this formula only to the change of heat, which is equal to the change of work. So heat is now directly converted into work. And since the piston receives the work shall be negative 730 because work is applied into the system rather than the system is generating the work. So that's why the value for our work or our heat now is minus 730. And because we are going to convert this into the second law of thermodynamics, which is entropy, we will now be using the formula delta S is equal to delta Q over the absolute temperature. And remember that work is applied into the system, so it is negative. Unless if the system is producing the work, that is positive. So that is negative 730 joules divided by the absolute temperature, which is 293 Kelvin. And so the value is also minus 2.49 joules per Kelvin. In other words, the entropy change is also negative. So the disorder of the gas that is decreased as it was pushed into a smaller volume. So now here it is actually associating the entropy with uh, our work that is produced, which is negative. So the disorder of the gas also decreases because the value is negative. Because as you decrease the gas, it tends to become more order, and so the randomness is actually uh, lessened. So by the value of minus 2.49 joules per Kelvin. So this is an example of a reversible process of our entropy. Now again, the ideal gas in this cylinder 21.1 here, there is the ideal gas inside the cylinder and is initially at the condition P1, V1, and absolute temperature 1. Now it is slowly expanding, meaning to say this piston is slowly expanding, meaning it is now producing its work from within. And at constant temperature, so it's expanding at constant temperature, meaning isothermal process, by allowing the piston to rise. So that is how it expands. Now its final condition will now be P2, V2, and T1 because the T1 here is always the same because it is constant temperature. So it's isothermal process. Now our V2 now will be 3 times of that initial V1. So V2 is now 3 times of our V1. Now find the change of this entropy, or find the entropy of the gas during this expansion. But remember that we are going to expect a positive entropy here because the piston is the one now that is producing the uh, work, and there is more randomness that is occurring within the gas. And so we have the mass of the gas is equal to 1.5 grams, and the M of the gas is 28 kilograms per kilomole for it. Now this is standard. This is already given. You don't have to worry about this value. And if you can still remember, the isothermal expansion of an ideal gas in our study about gases is given by this formula. So our work will now be equal to our change in Q. Now, there is no more change in internal energy because our T1 and our T2, which is also equal to T1, there is no uh, temperature change. So therefore, there will be no more internal energy change. So it's equal to P1 times V1 times V2 over V1 logarithm of that one. So this is already given in the previous topic about ideal gases. And so if we are going to calculate, we are going to have delta S, which is the entropy or the change of entropy, will now be equal to delta Q over T, because remember that delta Q is just the work. So that's the same thing. So delta Q over T is also equal to P1 V1 logarithm of V1 over V2. So we can calculate this out. We can substitute this out. And of course, that is also equal to M over capital M R times ln of V2 over V1. So these are all the conversions of this problem. So instead of writing this one, you can also substitute this one with this one, or maybe you can substitute this one with this one. This one is already discussed in the topic in ideal gas. So we can substitute instead, we can make use of this. So delta S is equal to 1.5, which is the mass of our gas, which is M, and over M, which is 28 kilogram per kilomole. That can be cancelled out, the grams. And so the value will now be equal to 8,314 joules per kilomole Kelvin. Okay, so that's the conversion. Then ln of our, remember, V2 over V1 is now equal to 3 times of the V1. So now the total value of our delta S will become 0.49 joules Kelvin. Now you see that the randomness is now positive, and of course the heat that is lost by our expanding gas due to its expansion is 0.49 joule per Kelvin, and that is our value for, or the value for our entropy.